So hello everyone, welcome back to machine learning technique sessions, and my name is Vaishali, assistant professor at Akgec Ghaziabad. So today this is the second session of machine learning techniques, and in this session we are going to discuss these concepts. First is the MAP hypothesis, maximum a posteriori hypothesis, then concept learning, then brute force based concept learning. So all related to the most probable hypothesis, and in all these concepts we'll see that we prefer the hypothesis which is most probable. Then the maximum likelihood and least square error hypothesis, and the last one is the minimum description length principle. So all these are the derivations. First we'll learn that what is the MAP hypothesis, then the concept of concept learning in machine learning, and then we'll see some derivations on the basis of the MAP hypothesis. So let's begin. First thing is maximum a posteriori hypothesis, or it is simply represented as HMAP. So the learner considers some set of the candidate hypothesis that is represented with the help of capital H. Suppose we are using this notation here, capital H, and it is the set or the collection of all the hypotheses, the number of the hypotheses or the solutions we are considering for a particular problem. So it is simply represented with the help of capital H, or the hypothesis space. So now we are interested in finding out this terminology, that is the most probable hypothesis, and small h represent individual hypothesis that we are considering that belongs to this capital H. So given the observed data D, it simply means that you are interested in finding out PH by D. Means after seeing the data, you are interested in finding out the probability of H, that whether H hold or not, whether it will consistent with the data D or not. So we have a terminology here called MAP hypothesis. It simply stands for the maximum or posteriori hypothesis, or the hypothesis which has most or high probability. So we can determine the MAP hypothesis by using the Bayes theorem. We have already studied what is Bayes theorem. It is nothing. It simply depends on the formula of conditional probability. So it's like PH by D, and when we use the conditional probability formula in terms of machine learning, then here comes PH by D, P D by H into P of H and P of D. So it is the posterior probability, it is the likelihood, it is the prior probability, and it is the marginal probability. So these are the certain terms which we use to refer these probabilities. So now HMAP is represented with the help of this notation here. So it is the PH by D. It is simply the posterior probability. Means after seeing the data set, you are interested in finding out that whether this hypothesis, the individual hypothesis, will hold or not. Argmax is the mathematical function which is used to maximize this particular probability. And here we are using this H belongs to capital H. So we are taking many individual hypotheses like H1, H2, H3, and capital H is the hypothesis space. It is a collection of all those individual hypotheses. In the very next step, we will expand this formula. We'll write posterior probability is equal to this, as we have seen here, that this is a simple conditional probability formula. We are just writing down H and D. Here we are discarding this term in the very next step. We are not considering PD. The reason is because D, or the probability of data set D, is constant for all the hypotheses. So by dividing a constant term will not impact in finding out the most probable hypothesis. So when we multiply or divide by a constant term, we can simply discard it. So in the very next step, we are not considering P of D. Then in the next step, we are saying that there is an assumption that every hypothesis in H is equally probable. Means if the probability of H1 is equal to 1 by 2, let's say, so the probability of H2 will also be 1 by 2. So That is what we mean by equally probable. Means P of hi is equal to P of hi. And now in this equation, we can easily discard this term P of h, because again it is the constant term. So in the end, we are getting, or we are left with P d by h. This is the likelihood. So P d by h is often called the likelihood of the data given h, because we know h here. And any hypothesis that maximizes this term is called maximum likelihood hypothesis, which is represented with the help of this notation, that is HML. So we are done with this concept HML hypothesis. Next topic is concept learning. So in machine learning, we learn this topic, that is the concept learning. It is a task of inferring a Boolean valued function. So these are the keywords, and I have just underlined these keywords like Boolean valued function from a set of the training example. So if we have some set of training examples, then with the help of concept learning, we are trying to infer some Boolean function out of it. The purpose of inferring is to use it as a general rule or the policy for classifying the unseen data. So concept learning helps us to frame some set of rules you can say, or some policies you can say. So with the help of which we can classify the unseen data in a better way. So in this, it will discover the general rules or the set of rules that you can apply to a particular concept, whatever you are trying to learn, whatever you are trying to classify. So the concept learning involves learning a function which is a rule from a set of the training example. This is the ultimate goal of this topic. So next we have brute force based concept learning. So brute force approach means that we are the approach in which we are just exploring all the possibilities, and it's base concept learning. So assume that a learner considers some finite hypothesis space, and that is represented with capital H. So defined over the instance space X. So these are the inputs we are having, and you just need to remember the notations that capital H is the hypothesis space, the collection of all the hypotheses which you are taking. Second, we have the instance spaces, that is x1, x2, x3, the inputs, in which the task is to learn this concept target that is represented x tends to 0 or 1. Well, that whether it will belong to the 0 or whether it will belong to 1. So as usual, we assume that the learner is given some sequence of training example, and always the training example is in this form. So the form is that x1 d1 means here we are taking the instance, and d it is the value you are providing. So x1 d1 is the target value, like 0 or 1. So x2 d2 x3 d2 till the m. Suppose you are taking m number of instances, so up to m you will give the examples, where xi is your some instance from the x and di is your target value for the xi. So if we have x1 and I am getting d1, so this is the input and this is the output, and the format in which you provide the example is simply x1 and d1 till xm to dm. So here the aim is to design a concept learning algorithm to output maximum of posteriori hypothesis. So here also we are talking about HMAP hypothesis. Now this is the brute force or map learning algorithm, and it simply involves 2 steps. It's a very simple algorithm. So first point says that for each individual hypothesis, that is the small h, we need to calculate the posterior probability. Posterior probability, or you can say the conditional probability formula, that is ph by d. It is, you can read it like, after seeing data d, what is the probability that h will hold or not? And this is your likelihood, this is the prior probability, and this is your marginal probability. So first is that you need to calculate the posterior probability for each hypothesis. Second, you need to output the hypothesis that is H map with the highest posterior probability. So you can represent it as H map is equal to argmax PH by D. Argmax, which is used to maximize this particular term here. Now here we are taking some assumptions. You can choose your probability distribution, that is PH, and PD by H in any way you wish. But to describe your prior knowledge about the learning task. So here let us choose them to be consistent with the following assumptions. So here we are considering some assumptions. First is whatever data you are taking, you are considering that the data is noise free. Second, the target concept which you are trying to learn, represented with the help of this notation C, is contained in the hypothesis space H. So you are considering that whatever you are trying to learn, the target concept is in there in the hypothesis, in the capital hypothesis. So we have no prior reason to believe that any hypothesis is most probable than the other. So you are ensuring that the probability of each hypothesis is equal. So given no prior knowledge here, that one hypothesis is more likely than the other. So if you want to calculate the probability of H, of the individual H, so it will be 1 divided by capital H. It is simple, the number of the favorable outcomes, probability of the number of favorable outcomes divided by the number of total outcomes. So it is for all the H in capital H. It is the hypothesis space containing all your hypotheses from H1 to till HM. So this is your prior probability here. Now, since we assume the noise-free training, here we are discussing the concept of consistency. Consistency means whether your hypothesis is able to classify all the instances in your data set accurately. So the condition here is we are deriving the values for PD by H, that is your likelihood here. So it will be 1 if your D is equal to H of X high, means the observed value is equal to the actual value is equal to the predicted one, the hypothesis X of I. So if it is so, then your value will be 1 if the data is consistent or your hypothesis is consistent with the data for all Di in the capital D. Here you are taking all instances, okay, all instances. And if not, if it is not equal to whatever you are assuming, so the value or the likelihood will be 0. Okay. Or you can say that the probability of data D given hypothesis H, that is the likelihood, is 1 if the D is consistent with the H or 0 otherwise. Okay. So it will have two values. So this is your Bayes formula, Bayes theorem or conditional probability formula. And now we are considering the two scenarios. So the first scenario is if the H is inconsistent with the training data, then your likelihood will be equal to 0. And if you put it as 0, then your posterior probability will be equal to 0. So this is a scenario where the H is inconsistent with the D, where it is not at all equal to the Di. Second scenario is when H is consistent with D. So when H is consistent with D, we have already seen that the value is equal to 1. So we simply put 1 here. Prior probability, we have already calculated that P of H is equal to 1 by capital H. So we put the value in the formula of Bayes theorem, and then PD. PD is your marginal probability. Then numerator is same, but denominator, we are writing denominator PD is equal to version space H, S and H. So here, why we are writing version space? Because here we are taking all the data points, but we are interested in only those subset of the hypothesis from the H that are consistent with the D. And here this term, that is VSH or the version space H, D, is used to represent that subset of the hypothesis which is consistent with the D. Okay, so now we can summarize the values for posterior probability. So here we have the posterior probability. The data, you have seen the data and now you are checking that your hypothesis will hold or not. So if H is consistent with the D, then it is 1 by Virgin space H comma D. Otherwise, it will be 0. If it is not consistent, then it will be 0. Okay. So now the next topic is maximum likelihood and least square error hypothesis. So here we are trying to prove that whatever the most probable hypothesis we get has the least square error hypothesis. So this is the theory you can read. Like many learning approaches such as neural network learning, linear regression, polynomial curve, they fitting try to learn a continuous valued target function. Okay, so here I'll focus on this term maximum likelihood hypothesis. So under certain assumptions, any learning algorithm that minimizes the squared error between the output hypothesis prediction and the training data will output a maximum likelihood hypothesis. Okay. Now come to the equation. We start with the maximum likelihood hypothesis definition, but using this smaller p to refer the probability density function because we are dealing with the continuous values. So here HML, we already derived this particular formula. HML is equal to argmax P D by H. So we assume a fixed set of training instances here. These are your instances. And consider that D to be the corresponding sequence of target value will be this. Means if your instance is this, then you are fixing that your target value will be D1. If it is X2, then it is D2. If it is XM, then it will be D of M. Okay, DM. Now we can write P D by H. This is your likelihood as the product of this because you are calculating it for each data value D1, D2 and everything. So here you are taking product. So argmax product I is equal to 1 to M, like D1 by H, then dot, we calculate the probability, then we will multiply it with the next one, that is D2 by H, and we do the same thing till the last. Okay. Next is here to derive the formula, we are using a distribution that is the normal distribution. So this is the equation for normal distribution. Here it is mean. Here it is mean, and the formula in the previous step we have HML is equal to argmax product of P D I H. So here in the place of DI, or you will expand or you will replace this with this. So here in the place of X you can write Di, and here in the place of mu you can write H, and in place of this now we will use the RHS side of the normal distribution formula. Okay, so here HML is equal to product of 1 by under root 2 pi sigma square. So this is the same thing, then exponential 1 by 2 sigma square, but in the place of x minus mu whole square becomes Di by mu whole square, or here in the place of mu we can write HXI. So as you can see here, this is the difference between the actual value, whatever actual value we have, that is the Di, the observed one, and this is the hypothesis, whatever you are assuming. So the difference, the square difference, and it should be the least. We have to derive this. So we now apply a transformation that is common in maximum likelihood calculation, and rather just doing or applying the operations on the product, we must convert it in some simple form. So we shall choose to maximize its less complicated log. So simply we'll apply the log, and accordingly our equation will become this. So these are some constant terms and we can discard these terms. So the first constant term is this 1 by under root 2 pi sigma square. We can discard this and we are left with this equation. Then maximizing, you can see here this is the negative and we are using a function called argmax. So the simple logic says that maximizing the negative quantity is equivalent minimizing the positive quantity. So you can write in the place of this argmax minus you can write argmin. You can use this term for this. So argmin and rest will remain same, but again this is the constant, so we can discard this and we are left with this particular equation here. So HML is equal to argmin, small h belongs to capital H, di minus h of xi whole square. Okay, so here you can say we can discard these values because they are independent of h. So with if you are including these things or not, it doesn't matter. So this is your final equation, and here you are saying whatever your maximum likelihood hypothesis has the least squared error. Minimum description length principle. Okay, so here the assumption is we need to represent whatever concept we are learning, that whatever concept we are learning in the minimum possible way, then it is said to be a good one. Okay, if we are able to represent the concept in the minimum possible way, then it is said to be a good one. That is the concept under the minimum description length principle. Now we have this particular formula. We have already seen this, that we can write H map is equal to argmax. This is the likelihood and this is your prior probability. You can simply apply the log to it and you'll get this. The product will convert into the summation, which is equivalent to this. If you are converting the max into the min, then you have to apply the negative. So this shows that the shorter hypothesis, the minimum length, are preferred following the minimum description length principle. Whatever hypothesis you are getting, the MDL, the shorter hypothesis, the minimum length is always preferred. So ultimately here you are concluding that HMDL, the hypothesis with the minimum description length, is equal to the hypothesis with the maximum or posteriori hypothesis. So maximum or the most probable hypothesis will have minimum description length. How? If we are considering an example here, suppose the problem of designing a code to transmit message drawn at random from the set D, where the problem of drawing the ith message is Pi. So while transmitting, we want a code that minimizes the expected number of bits. Obviously, we are trying to minimize the length. So when we talk about message, then it can be shortened if we minimize the expected number of the bits. To achieve this, we assign the shorter codes to the most probable messages, and in this way we are able to minimize the number of bits. So we represent the length of the message I as LCI, that is the length. So here the MDL formulation says this H map is equal to argmin LCH of H plus, and this is the conditional. So here we are using these notation CH. It simply represents the optimal encoding for hypothesis, and CD by H is the optimal encoding, whatever encoding we are using for D given data H. So if you compare this with this formula with this, so with the help of the information theory, if you place or if you substitute LCH is equal to minus log P, LCH is equal to minus log P, and H is same as you can see here. So you can equate these two, and with the help of these you can easily say that HMDL is equal to H map. So this is it for today, and in this session we have discussed that what is the concept learning, what is the most probable hypothesis, and some derivations on it.